The James Webb Space Telescope, JWST, launched on December 25, 2021, represents humanity's most advanced tool for peering into the cosmos. Designed to observe the earliest galaxies, stars, and cosmic phenomena, JWST has surpassed expectations with its unprecedented infrared capabilities. However, its discoveries are not merely illuminating the past, they are unraveling the very fabric of our understanding of the universe. Recent observations have revealed anomalies so profound that they challenge the foundational principles of cosmology, prompting scientists to question the Big Bang, the nature of time, and even the singularity of our universe. This article explores the unsettling findings of JWST, their implications, and the radical theories they inspire, expanding on the notion that we may be witnessing evidence of a reality far stranger than we ever imagined. One of JWST's most shocking discoveries is the detection of galaxies that appear to defy the laws of physics as we understand them. In 2022, astronomers analyzing JWST data identified a galaxy, dubbed Glass Z13, formed approximately 290 million years after the Big Bang. This galaxy, along with dozens of others observed at similar distances, is extraordinarily massive, bright, and structurally complex. According to the Standard Model of Cosmology, known as the Lambda Cold Dark Matter, Lambda CDM model, such galaxies should not exist so early in the universe's history. The Big Bang theory posits that the universe began 13.8 billion years ago, with matter gradually coalescing into stars and galaxies over hundreds of millions of years. Yet, these galaxies are too evolved, containing stars and structures that suggest a formation process far faster than current models allow. The Lambda CDM model predicts that the early universe was a sparse, chaotic environment with limited matter available for star and galaxy formation. Galaxies like Glass Z13, however, contain billions of stars and exhibit organized structures, implying a rapid assembly of matter. Theoretical physicist Dr. Julian Munoz, in a 2023 study published in the Astrophysical Journal, noted that these galaxies challenge the hierarchical model of galaxy formation, where small structures merge over time to form larger ones. The presence of such massive galaxies suggests either an accelerated formation process or a fundamental misunderstanding of cosmic evolution. Moreover, JWST has identified galaxies with unusually high metallicity, indicating the presence of heavy elements like carbon and oxygen, which are typically produced by multiple generations of stars. In a universe only 290 million years old, there should not have been enough time for such elements to form in abundance. This anomaly has led some astronomers to propose that these galaxies may have formed under conditions not accounted for in our models, such as enhanced star formation rates or unknown physical processes. Even more perplexing are galaxies observed by JWST that appear to convert 100% of their gas into stars. Typically, galaxies convert only about 10% of their gas into stars, with the remainder forming dust, nebulae, or remaining as diffuse gas. Yet, JWST has detected at least 3 galaxies, tentatively named zero-gas galaxies, that consist entirely of stars, with no detectable gas or dust. This phenomenon, reported in a 2024 Nature article by Drive Alison Kirkpatrick, defies every known model of galaxy formation, which relies on gas as the raw material for star formation. The absence of gas suggests either an unprecedented efficiency in star formation or that these objects are not galaxies as we understand them. These findings have sparked radical hypotheses. Some scientists speculate that these objects might not be galaxies at all but exotic structures, perhaps remnants of a pre-Big Bang cosmos, artifacts from a higher dimensional space, or even evidence of a multiverse. While such ideas were once relegated to the fringes of cosmology, JWST's data has given them new credibility, forcing researchers to confront the possibility that our universe's history is far more complex than previously thought. The JWST's ability to observe objects at the edge of the observable universe has introduced another layer of mystery. The observable universe is defined by the Hubble sphere, the region within which objects recede from us at speeds less than or equal to the speed of light. Beyond this boundary, the expansion of space causes objects to move away faster than light, rendering them theoretically invisible. However, JWST has detected light from objects that appear to lie beyond this cosmic horizon, challenging our understanding of space and time. The expansion of the universe, first discovered by Edwin Hubble in the 1920s, implies that distant galaxies are moving away from us at speeds proportional to their distance. The Hubble sphere marks the boundary where this recession velocity reaches the speed of light. According to general relativity, light from objects beyond this boundary should not reach us, as their recession velocity outpaces the light's ability to travel through expanding space. Yet, JWST's infrared instruments have captured light from galaxies that appear to lie in this forbidden zone. This phenomenon is possible because the observable universe is not static. As space expands, the light from distant objects, emitted billions of years ago, continues to reach us, even if the objects themselves are now beyond the Hubble sphere. However, JWST's observations suggest something more profound. The light from these galaxies carries signatures that do not align with expected redshift patterns. In a 2024 study published in Monthly Notices of the Royal Astronomical Society, researchers proposed that these anomalies could indicate variations in the expansion rate of the universe or the presence of unknown physical processes affecting light propagation. The detection of light from beyond the Hubble sphere raises a chilling question. Are we seeing the edge of our universe, or something beyond it? Some theorists suggest that JWST is capturing light that has traveled through regions of spacetime influenced by external structures, perhaps gravitational fields from another universe. This idea aligns with the concept of a multiverse, where multiple universes with distinct physical properties coexist. If JWST is indeed detecting signals from beyond our cosmic horizon, it could imply that our universe is not an isolated system but part of a larger, interconnected cosmic framework. Among JWST's most enigmatic discoveries is a faint, rhythmic oscillation detected in the cosmic background noise. Unlike known phenomena such as pulsars, gravitational waves, or cosmic microwave background (CMB) fluctuations, this signal, dubbed the heartbeat beyond time by some astrophysicists, exhibits a precise, repeating pattern that defies explanation. First reported in a 2025 Science article by Drive Priyangvada Nutrajan, the signal appears to follow a mathematical structure, suggesting it may be generated rather than random. The oscillation, detected in the infrared spectrum, has a periodicity that does not correspond to any known astrophysical process. Pulsars, for example, emit regular pulses but are tied to specific stellar objects, whereas this signal appears diffuse, permeating the background of the universe. Gravitational waves, detected by experiments like LIGO, have distinct signatures related to massive events like black hole mergers, but this signal lacks such associations. The CMB, a snapshot of the early universe's radiation, is isotropic and does not exhibit rhythmic patterns. Some researchers propose that the signal could be a signature of exotic matter or energy, possibly originating from outside our universe. For instance, it could be related to hypothetical particles like axions or dark energy fluctuations. Others speculate that the signal's mathematical precision suggests an artificial origin, though this idea remains highly controversial. While mainstream science avoids anthropocentric interpretations, the signal's regularity has prompted cautious discussions about whether it could represent a deliberate encoding from an unknown source. The discovery of this frequency challenges the isotropy and homogeneity of the universe, key assumptions of the Big Bang model. If the signal originates from beyond our universe, it could indicate interactions with external structures or dimensions. Alternatively, it might reflect a previously unknown property of spacetime, such as a periodic fluctuation in the fabric of the cosmos. Until more data is collected, the heartbeat beyond time remains one of JWST's most tantalizing mysteries, pushing the boundaries of what we believe is possible. Another unsettling discovery is the presence of gravitational anomalies that lack visible sources. JWST has observed galaxies at extreme distances that exhibit gravitational effects, such as lensing, where light is bent by massive objects that cannot be explained by the visible matter present. These phantom mass fields act like invisible forces, distorting spacetime in ways that defy current theories. Dark matter, an invisible substance thought to constitute 27% of the universe's mass energy, is often invoked to explain gravitational effects not accounted for by visible matter. However, the anomalies detected by JWST are too extreme to be explained by dark matter alone. In a 2024 Physical Review Letter study, Dr. Subir Sarkar proposed that these effects could indicate the presence of exotic mass fields, possibly originating from outside our universe. These fields behave like gravitational fingerprints, pressing on spacetime without a detectable source. The anomalies have revived interest in the concept of a shadow universe or mirror universe, where a parallel reality with its own physical laws interacts with ours. Proposed in the 1990s by physicists like Dr. Lisa Randall, this theory suggests that our universe might be gravitationally coupled to another, with effects manifesting as unexplained phenomena. JWST's observations of asymmetric particle behaviors and rotational patterns in distant galaxies lend credence to this idea, suggesting that our universe might be overlapping with another system where physical laws, including the direction of time, operate differently. Perhaps the most baffling discovery is the observation of a cosmic echo, a light signature from the edge of the observable universe that reappears after fading. In 2025, JWST's near-infrared spectrograph, NIR-SPEC, detected a light source that vanished, only to reappear with the same spectral fingerprint but from a different direction. This phenomenon, reported in astronomy and astrophysics, defies conventional explanations. There are two primary hypotheses for the cosmic echo. The first suggests that the universe is finite and closed, like a sphere, allowing light to loop back around its curvature. This would imply that the universe has a finite volume, contradicting the prevailing view of an infinite, flat cosmos. The second, more radical hypothesis posits that the light is reflecting off a physical boundary or structure at the edge of the universe, something capable of redirecting light across cosmic distances. The cosmic echo fuels speculation about a multiverse. If the light is reflecting off a boundary, it could indicate the presence of another universe or a higher dimensional structure. Theoretical physicist Dr. Michio Kaku, in a 2025 lecture, suggested that such a boundary might represent the interface between universes, where physical laws transition or overlap. While speculative, this idea aligns with string theory's prediction of a multiverse, where multiple universes exist within a higher dimensional bulk. The cumulative weight of JWST's discoveries has led some scientists, including Nobel laureate Dr. Roger Penrose, to question the Big Bang model itself. The presence of massive, evolved galaxies, signals from beyond the Hubble sphere, unexplained frequencies, and gravitational anomalies suggest that the universe may not have a singular beginning. Penrose's conformal cyclic cosmology, CCC, theory, which proposes that the universe undergoes infinite cycles of expansion and contraction, has gained renewed attention. In this model, the early universe observed by JWST might be a remnant of a previous cosmic cycle, blurring the distinction between beginning and end. Other theories gaining traction include the ekpyrotic universe, which posits that our universe emerged from the collision of two higher-dimensional branes, and the multiverse model, where our universe is one of many with varying physical constants. These models challenge the notion of a singular Big Bang, suggesting that what we perceive as the early universe might be a transition point between different cosmic states. Some researchers propose a more radical idea. The universe is not a linear timeline but a fracture, where multiple realities or dimensions intersect. The galaxies, signals, and anomalies observed by JWST could represent points of overlap, where the boundaries between universes or timelines become porous. This hypothesis, while speculative, offers a framework for understanding why JWST's data defies conventional models. The discoveries made by JWST raise profound philosophical questions. If our universe is not singular, if it interacts with others, or if it lacks a clear beginning, what does this mean for our place in the cosmos? The notion that we are not in our universe, as suggested by some scientists, challenges our sense of reality. Are we part of a larger, interconnected multiverse? Is our universe a shadow of another, or a fleeting moment in an eternal cycle? These questions transcend science, touching on existential themes about existence, purpose, and the nature of reality. Some fringe theories even suggest that the heartbeat beyond time and other anomalies could imply a form of cosmic intelligence. While mainstream science dismisses such claims, the mathematical precision of the detected frequency has prompted speculation about whether the universe itself could encode information in ways we do not yet understand. This idea, while far from proven, underscores the transformative impact of JWST's findings on both science and philosophy. The James Webb Space Telescope has not only expanded our view of the cosmos but also shattered our assumptions about it. As scientists continue to analyze its data, new questions will emerge, and old certainties will crumble. Future observations, combined with advancements in theoretical physics, may clarify whether we are witnessing the edge of our universe, the shadow of another, or something entirely beyond comprehension. JWST's mission is far from over. Planned observations through 2030 will focus on refining measurements of distant galaxies, searching for additional signals, and mapping gravitational anomalies. Collaborations with other observatories, such as the upcoming Vera C. Rubin Observatory, will provide complementary data to test emerging theories. Additionally, advancements in quantum cosmology and computational modeling may help simulate the conditions observed by JWST, offering insights into their origins. The discoveries of JWST demand a willingness to embrace uncertainty. Cosmology, once anchored by the Big Bang and the Lambda CDM model, is entering a new era of exploration. Scientists must be open to revising or even abandoning long-held theories in light of new evidence. The universe, as revealed by JWST, is far stranger and more complex than we ever imagined. The James Webb Space Telescope has done more than peer into the past. It has unveiled a cosmos that challenges our understanding of reality. From impossible galaxies to mysterious signals, gravitational anomalies to cosmic echoes, its discoveries suggest that our universe may not be singular, linear, or even ours. As we stand on the precipice of a new cosmological paradigm, we must confront the possibility that we are part of a larger, more intricate reality, one that may hold answers to questions we have yet to ask. The cosmos has blinked back, and what it reveals may change everything we believe about existence.